but can I apply L'Hopital's rule again? Is this an indeterminate quotient? Yeah. Top side towards infinity, bottom side towards infinity. So I can apply L'Hopital's rule again if I feel like it. And you're going to have a lot of questions, so I'll have it applied many times. So through L'Hopital's rule, it's now the same limit as x goes towards infinity, but of the respective derivatives. So 8 over 16, but that's constant. So the answer is 8 over 16, which is half like described earlier. Okay. Now, I'm bringing very simple cases here, polynomial or polynomial, which already know a rule for anyway, so it seems not that worthwhile. But the amount of limits you can now tackle has greatly increased with this rule. Yeah. So let's try one in the textbook. Let's try number 15. Again, with number 15, you should know what to do. Should, probably don't. Way of grading your last exam on this trigonometric limit here. But now this trigonometric limit is ridiculously simple in comparison with the algebraic chicanery you had to play before. 3 sine 4x over 5x. 3 sine 4x over 5x. If you were stuck with the games we played before, what would you have to do? You'd have to get a 4 down here next to the x. So I'd multiply top and bottom by 4. Right? This is what we would have done. We multiply top and bottom by 4 and pulled out the 3 and the 5. So I'd have a 12 fifths on the outside. You guys don't know what I'm doing or whatever. Sine 4x over 4x. That's what you would have had to do. You'd have to see how to do that. What are you looking for? You're looking for that limit, right? The input's the same as the denominator, and x heading towards 0. So this limit is now what? So you don't even know. One person knows, right? One remembers. So that whatever. So that's 1. Yeah, just like you caught me the other day. Whatever. So 1 times what? 12 fifths, right? So 12 fifths times 1, 12. That's what we had to do. Play these tricky games with that. No, we're gonna compare with that one limit we happen to know about sine, right? But now what can you do? So you don't want to do that because it's horrible in comparison with the ease of L'Hopital's rule. So you have 3 sine 4x over 5x. First check. Is it an indeterminate quotient? Is it a 0 over 0 case? Is it an infinity over infinity case?
Yes.
Which one?
0.
It's a 0 over 0 case, so we can apply L'Hopital's rule. Please do not apply L'Hopital's rule willy-nilly. You have to make sure it truly is 0, 0, infinity over infinity. People start just applying it randomly and start taking derivatives on every single limit they ever see after they see this section. Make sure it's always indeterminate form, all right?
The sine is 0, 1?
Sine of 0? 0. Sine of 0, 0. That's why this is a 0, 0 case. As x is close to 0, this expression goes close to sine of 4 times 0, which is sine of 0, which is 0. So it goes very close to 0. So does the bottom. So I should apply L'Hopital's rule and take the derivative top and bottom. So the derivative of the top is what? 4 is going to pop out and give me a cos 4x, correct? So I have the limit as x goes to 0 of 12 cos 4x. The derivative of 5x is 5. Now run the limit again. What is cos 4x heading to as x goes towards 0? 1. And so we get 12 fifths times 1, which is 12 fifths. I didn't have to play any algebraic games, right? Much more efficient.
Okay, I got 2 questions.
Yeah.
First, how do you know whether it's a 0 over 0 or an infinity over infinity case?
So you are simply taking what x is heading towards and just put it in there, basically.
Okay.
Put it in there. So sine of 4 times 0 is sine of 0. That's 0. 0 times 3 would be 0. The top is heading towards 0.
Okay.
Here, as x goes towards 0, it's heading towards 5 times 0, which is 0. So the top and bottom both heading towards 0.
So if in the case of number 13, if it was x going to 1, then it wouldn't work?
Correct. You could not do this process right now. It will, in general, not yield the correct answer.
Now, does it also work for when x is any number as long as it gets 0?
Yes. X can head towards anything. That's why I use A over there. As long as these things head towards 0 or both infinities under that condition.
Okay.
0 over infinity is not indeterminate, right? If you have something where the top is heading towards 0 and the bottom is heading towards infinity, what is that heading towards altogether?
DNF. I mean,
0. Heading towards 0, right? The top's heading towards something ridiculously tiny. The bottom's heading towards something ridiculously large. That is heading towards 0. Okay? Infinity over 0 is not an indeterminate form. the top is getting super colossal, and the bottom is getting super tiny. What's it heading towards? Infinity, right? Those are not indeterminate. I just determined them, all right? So it's only 0, 0, and infinity, infinity that you're looking for here, all right? Any mix of the two, the zeros and infinities, is not indeterminate. Got it? Roger?
The derivative of 2x.
Yeah.
Still got 2x. Same.
Yeah, here, x goes towards infinity, so when you have a polynomial, the leading term dominates.
So what if it is derivative of 2x?
If this were negative here, then the answer would become negative 2/3 at the end. Yeah. In either way, whether you look at it as just, you know, they have the same power, they have the same degree, so it's the ratio of the coefficients, or you take the derivatives, you would get the negative in there. It'll be in there.
I thought sine of 0 is 0 because it's heading towards.
Sine of 0 is 0, that's correct.
Yeah, so. I mean, no, I thought
So
sine of 0
this is heading towards 0, and this is heading towards 0. We can apply, well, how else what we did. Right.
Can you just say how you got the 12 cosine?
I took the derivative of sine 4x. So when I do that, I get cosine of 4x times the derivative of the inner 4x, which is a 4. So I get that extra 4 multiple out here, making it a 12. All right, just a quick chain rule.
Yeah, how'd you go from 12 cos 4x to 12 times 1?
Oh yeah.
So this?
Yeah.
Yeah.
Because as x goes towards 0 here, if this little guy heads towards 0, not 6, 0, 4 times 0 is 0, cos of 0 is
1.
right.
Okay.
So got it right.
Okay.
Okay, so again, L'Hopital's rule applies to quotients. We're going to have other indeterminate forms besides quotients in a moment, and we're going to change them into quotients so you can use L'Hopital's rule. Let's do a few more of the quotients first. Number 18, another trig one. I hope that doing the trig ones helps you appreciate the simplicity of this over what we had to do before. So 18. Limit of tan 7x over tan 4x. We would have had to write tan in terms of sine and cos and apply the one limit we know about sine x over x for this thing. And this is z heads towards, I use z, whatever, I use x towards 0. So, is it an indeterminate form, yay or nay? Yes. What is tan of 0?
0.
Okay, so it's a 0, 0 case, correct? So apply L'Hopital's rule. What's the derivative of tan? Secant squared. So we have the limit of secant squared 7x times the derivative of 7x, which is 7. That's the top. Same thing at the bottom, so I have secant squared 4x times the derivative of 4x, which is 4, as x heads towards 0. What does secant head towards as its input heads towards 0? What's secant of 0?
Cosine of sine.
1. That was correct, it's 1. Right?
So you gotta stop right there.
Am I supposed to stop? The answer's 7/4. That should be done. How do you know secant of 0 is 1?
Oh, it's 1 over cosine.
It's 1 over cosine. And cosine of 0 is 1. What's 1 over 1? 1. Alright? So now you know the answer is 7/4. Right? Because the secant squareds are both heading towards 1 as x goes to 0. Right? So one round of L'Hopital's got you your answer very quickly. Yeah.
Did you do one with trig function with infinity as x is approaching towards infinity?